Okay, good morning. So this material that we're starting today is not included in next week's quiz. We now are going to be talking about oligo and polysaccharides, which are structures that contain multiple sugars bonded to each other. So we discussed what we called a hemiacetal as the bond that exists in a cyclic structure that's a monosaccharide. If you recall, the way that we identify these types of linkages in ring forms of sugars is that you're looking for a carbon that is simultaneously bonded to two oxygens. One of them is an OH, the other one is an ether, technically, right? So an alcohol and an ether, meaning an oxygen bonded to another carbon, which is what you see here in this cyclic form of glucose. This carbon, which is what we call the anomeric carbon, is the one that is simultaneously bonded to an alcohol and then also simultaneously bonded to another oxygen that itself is bonded to another carbon. That's what makes a hemiacetal. Okay, now we had a brief discussion about what an acetal is. Remember, hemi means half of whatever. If you think about a hemisphere, right, the northern hemisphere versus the southern hemisphere of the planet, it's half of the sphere, which is the whole planet, right? So when you're talking about a hemiacetal, it's because you're talking about what we technically refer to as a half of an acetal. So what is an acetal? We had mentioned this briefly. Let's sort of recap what it is now. How do you recognize an acetal? So an acetal is a carbon that's bonded again to two oxygens, but both of those oxygens are bonded to another carbon, okay? So if you take a ring structure like the one shown here, that's the cyclic form of glucose, if that structure reacts with another alcohol, here shown with the simplest of all alcohols, which is methanol, what happens is that there's an exchange process that happens with the ring structure. The mechanism is beyond the scope of this course. And those of you who are in organic chemistry are going to see this, but here we're just going to sort of do the magic behind the scenes. There's an exchange process in which that OH is exchanged for this piece of the alcohol, and then the OH that was originally on the sugar with the hydrogen of that alcohol, these two come together to form a water molecule that simply goes away. The other component, the alkyl group, alkyl chain plus the oxygen, will replace that hydroxy group on that anomeric carbon. So if you notice now, this oxygen is bonded to carbon, and this oxygen is also bonded to carbon. So this linkage, this structure, sort of based on what we drew here as a little cartoon, that is an acetal linkage. Now, in the context of sugars, because as I've mentioned several times, carbohydrate biochemists have their own lingo for things. That type of linkage is known as an acetal in the bigger world of organic chemistry. In the smaller world of carbohydrate chemistry, that type of acetal linkage is called a glycosidic bond. It's what joins two sugars together. Sugars are when they're combined with each other are called glycosides, which is what is shown here, this term, right? And then when they are linked with one another to form multiple structures, we call that the bond that links them together, we call them a glycosidic bond, because that's what joins them together. Now, in this example, this is not a sugar. This is just a simple alcohol reacting with a sugar, right? But at the molecular, if you really zoom into this, it's the hemiacetal that's reacting with another alcohol to then form the acetal linkage. Now, if you pay attention to the structures of sugars, sugars have a multitude of alcohols as part of their skeleton, as we've already discussed. Sugars are by definition aldehydes and ketones with multiple alcohols scattered throughout them. When they're in cyclic form, the aldehyde or ketone is masked in the form of a hemiacetal, But still, what happens is that these hemiacetal structures now, when they're encountering another alcohol, which can be as simple as the simplest of them, which is methanol, turns out it can also be another alcohol coming from another sugar. And that's what we're going to be talking about now. How is it that sugars come together to ultimately form oligosaccharides and ultimately polysaccharides? So if you look in nature, there's a whole bunch of different of these types of glycosides, not necessarily two sugars. So the methanol example is the simplest example that could be done in the laboratory. But if you actually look in nature, there is a whole bunch of different glycosides out there that involve sugars being linked with other structures or entities, forming these types of acetal linkages. So here's an example of one. This is one of the compounds that can be found in the vanilla bean. And the structure that's bonded to the sugar, in this case it's glucose, down, up, down, right? That's that entity here. If it actually goes in the opposite direction than what we were talking about on the previous slide. So in the previous slide, we were speaking of a hemiacetal reacting with an alcohol to form an acetal. Notice these reactions are reversible. You could start with an acetal, treat it water, or have it react with water, and then the reaction actually goes in the opposite direction. So depending on which one is more abundant, if the water is more abundant than this alcohol, then the reaction is going to the left. If you have boatloads of the alcohol and not much water in the pot, then the reaction is going to the right. Remember, biology does what it wants. So what biology does is that this substance that exists in the vanilla bean, which is actually made starting with this compound plus the sugar to the left, this is one way in which these beans store this compound sort of attached to glucose. So when we harvest the vanilla beans and we utilize them in our foodstuffs, it turns out that the active ingredient that gives vanilla extract, its flavor, is this compound that is hydrolyzed. Anything that involves breaking something into pieces by the actions of water is called a hydrolysis reaction. Lysis is breakage, hydro by means of water. So this compound that is released, which is called vanillin, that's actually what gives vanilla extract its odor and its flavor. When you actually purchase artificial vanilla extract wherever it's available, this is what they're making it with, because it turns out in the natural vanilla extract from real vanilla beans, it's still the compound that's in there that's giving that concoction that's naturally obtained, that this is the compound that's giving the vanilla extract its flavor and odor. In the artificial version, they're simply taking the compound that's been synthesized in the laboratory or even harvested from nature and simply, isolated and stored and sold in bags or buckets. And then they take that and they mix it with other things to mimic what would be vanilla extract that's obtained from the natural vanilla beans. But this is the compound that is giving you that flavor, right? So if you notice, it's an alcohol. Here's the hemiacetal of the glucose. So technically, if this were going to the left, this is what happens in the plant. The plant takes glucose, the plant makes the vanillin, and it combines it with the glucose, right? And it produces the vanillin glycoside. Notice here the hemiacetal that's latching those two together. This linkage, which is an acetal, we call it a glycoside, okay? When we harvest the plants, we're doing it in the opposite direction. We're hydrolyzing these glycosides to then produce the vanillin, which is what gives the vanilla extract its odor and flavor, as I've been saying. So a couple of things that we need to pay attention to when we're looking at these structures. Again, down, up, down means this is coming from glucose, right? If this one's up, this is coming from D-glucose. And then if you look at this carbon and the oxygen that's attached to it, it's pointing upward in the same direction as this. This is a beta glycosidic bond. So now we can speak of this as a beta glycoside because the linkage that is the acetal over here is part of a beta anomer, right, of two possibilities. That vanillin piece can be up or down. Because it's up in the same direction as the CH2OH, that's a beta linkage, and we call that a beta glycoside, okay? All right, so here's another example. This compound on the right, which is called salicyl alcohol, is a derivative of salicylates like aspirin and salicylic acid and things of the sort. That one is also a naturally occurring compound. There are certain plants out there that will produce this salicin compound. Salicin is nothing other than glucose, D-glucose, in a beta glycoside linkage with the compound, right? The salicyl alcohol. And it's actually been known for a very long time that if you take the bark of this tree, or it's a plant where this is coming from, and you chew it, you get some of these analgesic and other similar pharmacological properties associated with aspirin because they're structurally related. So, of course, we now in 2020 know all kinds of things about pharmaceuticals and developing them and making them in the lab and all these things. In the early days of chemistry, where there was no such concept, people relied on going out there and chewing leaves of plants and concocting things with barks of trees and roots and all kinds of different things. Well, they didn't understand what was happening because they didn't have the tools and the technology to be able to assess what was in there. But in many of these natural concoctions that are out there in naturopathic medicine and things of the sort, many of those substances that are coming from natural sources contain things like this that ultimately are released these compounds that are linked to one another in different ways. And this is one example of how these glycosides that exist in nature are providing these compounds that have been known for a long time to provide relief of this or cure of that. It's because they contain these compounds that are linked to other biological structures, and these serve as the storage forms and serve as the vehicles to deliver these things that we can then harvest. So what happens if the alcohol, the second alcohol, is not a salicyl alcohol, or it's not a vanillin, or it's not a methanol, but it's actually another sugar that is providing one of its OH groups, of which it has many, to then form the linkage, right? So here's an example of a glucose. We know it's glucose because it's down, up, down. Here's another glucose, down, up, down, right? This one happens to be alpha, because if you notice, this is down. This is alpha D-glucose, right? And so is the other one. So this one and this one are alpha D-glucose. So what happens if this alcohol on carbon number 4 of 1 glucose serves as the alcohol with which the hemiacetal of the first one that's on the left does the exchange? So what happens is then that the skeleton of the one on the right becomes attached to the skeleton to the one on the left, right here in the middle. This is turning into a big old mess, so let me just clean this up. So this piece is the alcohol exchanges for this, right? And then the OH and this H end up as water, and this whole big thing ends up attached to this whole big thing. Well, this is what we have here, okay? Here's the glucose that was on the left. You can see down, up, down. The linkage is still alpha because that oxygen coming off of this carbon is in the opposite direction as that CH2OH, which is what defines it as a D sugar. And then if you look at the second sugar, its skeleton is still intact, simply that what was its alcohol is now linked to the other sugar in this type of hemacetal linkage, okay? So you can see, let me highlight this again, this here is a hemiacetal. Why? It's a carbon bonded to one oxygen and a second oxygen. Both of those oxygens are bonded to another carbon. And this is what holds these two sugars together. Now, you need to pay a little bit closer attention as to, again, which carbons from each sugar are bonding to each other and what type of glycosidic linkage it is. It can either be alpha or beta. The reference point is always the acetal, and the sugar that is providing that anomeric carbon in the the acetal. The sugar that's providing that acetal, i.e. glycosidic linkage, that's the one that's the reference point to describe whether the linkage is alpha or beta. And then you have to actually indicate which carbons are involved in the two sugars that are forming the linkage. So in this case, we call this, and if you zoom in into the file that I'm sharing, we call this an alpha, and the way that we do it, let me do this again, is alpha with a dash, and then you put in parentheses the origin, the sugar that's originating from, which is where the acetal is originating from, and then which carbon on the second sugar it's going to, right? So we call this an alpha 1,4 glycosidic bond. So again, why is it alpha? This is pointing upward, this is pointing downward, so they're in the opposite direction. This is what makes it alpha. And it's 1,4 because it's coming from carbon 1 on this sugar, carbon number 1, which is the one that is the hemiacetal. I keep saying hemiacetal, the one that is the acetal, the glycosidic bond. And then it's going towards carbon number 4 in the second sugar, okay? So notice this piece is still a hemiacetal because it has not been involved in any way, shape, or form with the formation of the glycosidic bond with the other sugar. That glycosidic bond could have been formed with this OH. In that case, we would have called it a 1,2 bond. It could have been with this one. That would have been called a 1,3 bond. But because it formed with carbon number 4, coming from carbon number 1 on the one that contains and is forming that acetal linkage, then it's 1 to 4, and it's alpha because of this reason. So this structure, which is called maltose, is a disaccharide. Why is it called disaccharide? Because it contains two sugars over here. They are linked together by a glycosidic bond. So one sugar, two sugars. That's why it's called a disaccharide. Okay, as shown up here. And then how are they held together? Specifically in maltose, they're held together by an alpha 1,4 glycosidic bond. Okay, so when you ingest starches, as we're going to learn in this piece that we're talking about here, we're going to talk about starches. When you ingest starches, the starches become partially hydrolyzed, and that starts in the mouth. The saliva contains amylase, which is an enzyme that starts hydrolyzing starches from the moment you ingest them. And then that partial hydrolysis produces oligosaccharides, of which disaccharides are the simplest. They contain two sugars. So maltose is a product of the partial hydrolysis of starch and glycogen. Starch is plant starch, which is two kinds we're going to learn in this lecture. And then glycogen is animal starch. Turns out animals also make a type of starch. We're going to talk about that. So when you ingest maltose, it actually gets hydrolyzed. Here they're sort of drawn in the opposite direction. But the two glucoses that are forming the maltose actually get fully hydrolyzed ultimately in the intestines to two free glucose molecules that then are ultimately absorbed by mechanisms we're going to talk about. Okay, so again, the alpha means how the first sugar that is providing the acetal linkage, how the anomeric carbon is arranged in that one. Again, opposite means alpha. And then the 1,4, again, means coming from carbon 1 on this one, latching on to carbon 4 on the other one. We're going to see all sorts of different types of linkages. And then if you stand back, you have to be able to analyze which two sugars are linked with each other, right? So this is down, up, down. This is glucose, and it's D-glucose, and it's alpha D-glucose, right? The one on the left, it's down, up, down. So it's glucose, right? We already know this because we've already analyzed it, but I'm doing it again just for emphasis. This is the D-glucose. And then if you observe, this is down and this is up. So this also came from an alpha D-glucose. So it's an alpha D-glucose bonded to another alpha D-glucose. How are they bonded? Alpha 1,4 glycosidic bond. Okay? So that's maltose. So if you look at the other end, the one that is not involved in anything, this is still a hemiacetal, right? It's not involved in any type of linkage other than closing up to form the ring. So remember, anytime you have a hemiacetal, that has the potential to open up. If the aldehyde is released, that is what becomes what we call a reducing end, right? And then it can rotate and close in the opposite direction, right? This here is now beta. Over here, this is still alpha. So it turns out that even though the acetal has been incapacitated, and this is one of the major features of the glycosidic, i.e. acetal linkage, those are fixed. Once it closes and it forms this structure like this in the alpha, it's stuck in alpha until the whole thing is broken down by hydrolysis or whatever. But hemiacetal has the ability to open and reclose and reopen and reclose. This process is continuing. Let me clean this up. This opening and reclosing, it's a constant back and forth. So this end is still reducing because it's a hemiacetal, and it's reducing because it's going back and forth, and in doing so, it's going to be exposing that aldehyde, which is what makes it reducing, meaning if you treat it with Benedict's reagent, it's going to give you a positive result. But it's due to this piece. This piece has nothing to do with that. The acetal linkage is actually very, very stable, very, very sturdy. It's the hemiacetal that is liable to not liable, labile, meaning, well, it's liable to breakage, but that means that it's labile. It can very easily open and reclose and open and reclose, and when it opens, it can be one or the other, right? Alpha or beta. So these simple disaccharides, in fact, simple oligosaccharides, they also exhibit this phenomenon of mutarotation, and it's at the reducing ends, at the hemiacetal ends. And as long as this piece is not too big, which is what happens with the small oligosaccharides, you can still detect these types of small oligosaccharides using Benedict's reagent, okay? All right, so we now need to start talking about some physiologically important compounds, now looking at them, they're a little bit bigger than just simply glucose and fructose and whatnot. So one of them is called cellobiose. Cellobiose is a constitutional isomer. Actually, it's a stereoisomer if you actually look at it carefully, because what the difference is that one's alpha and the other one is beta. Let's just call it an isomer for now. The structure is isomeric with maltose. And the difference is that the linkage between the sugars is no longer alpha, but it's beta. So if you notice here, not there, sorry, I circled the wrong thing. If you notice, well, yes, here, because I want to make the reference point. This is beta now, right? It's still 1,4 because it's linked on the same carbon. But if the glucose on the right, we know it's glucose because it's down, up, down, right? If the glucose on the right does that exchange with the hemiacetal, not with alpha glucose, but with beta glucose, then what ends up happening is that you have this beta glycosidic bond over here, right? This beta glycosidic bond. This is moving upward, and this is upward. That's what makes it beta. So we call it a beta 1,4 glycosidic bond, and this is what joins together these two sugars. So it turns out we do not have the enzymes that can actually break down beta 1,4 glycosidic bonds. And this is actually a product of the bacterial microorganism directed hydrolysis of cellulose. Cellulose is the fancy word for dietary fiber. We're going to talk about the structure of cellulose as well. Now this end, because it's a hemiacetal, this, like maltose, can undergo mutarotation because that can open and close back and forth, right? So this piece is what allows the structure to still exhibit mutarotation, which means it's going to be positive if you throw it at Benedict's. But this piece, because it's fixed, nothing happens there. This is just simply an alternative arrangement of the two sugars bonded together, okay? All right, so lactose is one that's critically important in human society. This is the main sugar in milk and all of the foodstuffs that are derived from milk, all milk products, dairy products. So what happens in this one is that there's a galactose down, up, up, bonded to a glucose down, up, down, okay? And the bond is a beta linkage, okay? Now, I need to take back partially what I said in the previous slide. I said that we do not have the bonds to break beta 1,4 glycosidic bonds, and I neglected to say that specifically in the case of cellulose. We do have a specific enzyme that is called lactase. The lactase is a beta galactosidase, meaning it recognizes specifically galactose bonded to glucose in a beta 1,4 linkage. Okay, so it's very specific. That's why it's called lactase. We're going to look at naming enzymes a little bit later. It's lactase because its only substrate is lactose. That's it. And lactose contains this beta 1,4 glycosidic linkage. That enzyme is what ultimately hydrolyzes lactose that comes in the diet. So when you drink milk, when you eat cheese, which includes sandwiches, pizza, when you eat ice cream, anything that comes from any type of milk product, there's going to be lactose in that substance. So it turns out, you probably have already heard or learned, you may know somebody, pretty much, this is not an uncommon disorder. Some people are what we call lactose intolerant, okay? And what happens is that they're either born with a genetic deficiency in the enzyme. It's a genetic disease, and that it's not really a disease, it's just a disorder. The person cannot ingest milk products because what happens is that they do not have the beta galactosidase that is responsible for breaking down the lactose. And this actually happens in the intestines. This is not an enzyme that's in your blood, it's in the intestines. So this is what allows, when you take these products, it's broken down into galactose and glucose, and then the two monosaccharides are absorbed. If you don't have an enzyme, you can't break down lactose, it lingers in the intestines. And at that point, what happens is that it just keeps traveling down the intestines, unhydrolyzable by humans. So bacteria, microorganisms that exist in your intestines are then taking down the lactose, and they're the ones that are breaking down the lactose into other things. One of the things they also do, in addition to breaking it down into those components and utilizing them, is that they actually will metabolize the lactose, and that will then produce other substances, ultimately producing bloating, flatulence, diarrhea, all sorts of problems, which is what lactose intolerance is associated with. So it can either be genetic, it can also be acquired, it turns out. There are certain, if you actually don't eat much milk products, if you don't eat cheese, if you never drink milk, over time, because of non-exposure, your body simply doesn't respond well, stops making the lactase properly. There's all kinds of issues and explanations for the fact. It's probably a combination of different factors, but you end up becoming lactose intolerant. We call it an acquired lactose intolerance. And then it turns out there's also certain ethnic populations that, for whatever reason, even if they eat and drink and whatever dairy products, it happens to be that certain populations over time can, in fact, lose the ability to hydrolyze the lactose because they lose the lactase for reasons that are entirely unclear, although it's been identified with certain ethnic populations. And then they just, that's when the point you may have heard of a cousin or an uncle or whoever that suddenly needs to start taking these little lactate pills. You can add to milk. You can actually now buy milk that has lactose free because the lactose has been hydrolyzed during the processing of the milk to completely get rid of the lactose. You can also buy little pills, or you can buy little dropper things that you add into milk or other things, and then it actually is providing the lactase, the enzyme that you can then eat the product. So again, if I know a couple of people that when we're going out for pizza or whatever, let me take a couple of lactate pills for the half hour before we're going out, and then they're all set to eat their pizza or eat their ice cream or whatever it is. And it doesn't completely relieve it. Some people still have, moderate or mild signs and symptoms, even after taking these things, but it's not as bad as if they didn't take it at all. Okay? All right. So sucrose is an interesting compound. Sucrose is the regular table sugar that we're, using every day to sweeten our things and whatnot. So sugar, in table sugar, which is sucrose, it's an interesting linkage because what actually happens is that it's a glucose and it's a alpha linkage coming from the glucose. But it turns out that the alcohol of the fructose that is being provided to link to the glucose is also the one that is on the anomeric carbon, i.e. coming from its own hemiacetal. So it turns out that both anomeric carbons are the ones that are involved in this linkage. And in this case, it's a little bit more complicated to designate it. So we call it an alpha-1 beta-2 glycosidic bond. For whatever reason, glucose is given the priority and it's named first. So again, from carbon 1 in glucose in an alpha linkage, that then is linking to carbon 2 in fructose. Remember, if you remember the open chain of fructose, there's a CH2OH, and then is where the ketone comes up, right? So carbon 2 is the one that ultimately forms the hemiacetal in fructose. So here's the CH2OH over here. It's carbon 2 that's involved in the hemiacetal in the fructose. So what happens is that the hemiacetal of the fructose reacts with the hemiacetal of the glucose. That's where the exchange happens. The water is released, and then both anomeric carbons are what are involved in the linkage. So then we call it alpha 1 beta 2, and then of course you don't have to say it this way. It's actually better to simply say alpha beta 1 to 2. We use 2 out. Let me do this again, because on the top it says something, but it's actually better what it says on the bottom. Okay, so the way that is typically represented is that it's an alpha beta bond, alpha to beta, and then we say that it's a 1 to 2. Here we use a double-headed arrow because it's coming back and forth between the two anomeric carbons. So it's an alpha comma beta 1 2 glycosidic bond. And then you can see here, again, alpha because they're in opposite directions. This is what defines the D form of the fructose. Notice this is now upward in the same direction as this. That's why it's a beta linkage coming from the fructose. It's an alpha linkage coming from the glucose, and it's from 1 on one and 2 on the other. Okay? So because there's no reducing end in this structure, given that both hemiacetals have been taken away, if you will, if you go back to all of these ones that we've been looking at, lactose still has a hemiacetal. This is a reducing end, right? This exhibits mutarotation. It can rotate, open back and forth, open, close, open, close, open, close, because it has an OH there. But in case of fructose, they're gone. They're both gone. So there's no possibility. So if you throw Benedicts to sucrose, nothing will happen. It's going to give you a negative result. So you should have learned this in the virtual lab that you had, that of the several disaccharides or oligosaccharides that are out there, sucrose is a unique link in which both hemiacetals are gone, and therefore there's no possibility of this mutarotation process, which involves the opening and the exposure of the aldehyde. Therefore, the sugar is non-reducing, okay, non-reducing. All right, so let's just talk a little bit about other types of oligosaccharides that are of relevance when speaking of digestion and how the body handles them in terms of as they're traveling through the intestines. And then, as I mentioned, we have a multitude of microorganisms in our intestines. And I don't know that you knew this, but there's more. I think I've mentioned this before. There are more bacterial cells in the human intestines than there are human cells in the human body. So we are loaded with microorganisms. They're very important. They're very friendly. We need them to be able to live because they help us with all kinds of things, including digestion and whatnot. So there are a series of foodstuffs that are notorious for producing gastrointestinal signs and symptoms associated with flatulence and bloating and, you know, all kinds of different GI symptoms. And it turns out it's because of the types of linkages that they contain that we sometimes are unable to properly digest them. And then even if we are, the multitude of microorganisms that exist, it's because the bacterial cells are much smaller than the human cells. They're very, very small. They don't have the sophistication that our cells do, and therefore they're very small. So because they're much smaller, you can have many more of them. And it turns out the number of bacterial cells surpass the number of human cells in the human body. It's an interesting phenomenon. So these bacteria also are technically competing with us for the foodstuffs that enter our intestines. So they're taking things in as well, and they're doing their own thing, right? So it turns out, as everybody probably is aware, legumes like peas and beans, right? Everybody's aware with beans that can be associated with these signs and symptoms that are, you know, not very pleasant. And it turns out that these particular sugars are the ones that are associated with bloating and whatnot because bacteria metabolize these sugars coming from these stuffs, and then they produce gases as part of that process. And that's what then leads to the bloating and the flatulence and things of the sort. So let's analyze the sugar that's here so that we can start being able to figure out what type of linkages are present. So first of all, we need to identify the specific monosaccharides that make up this sugar. This one happens to be called raffinose. So if you observe down, up, it is which one? Can anybody type the name of that one as I take a sip from my tea? Nobody? Down, up. So this piece is galactose. You need to start recognizing these things because you're going to get asked on the exam, on the quiz, FYI. It's D-galactose because this is up. And then what type of linkage? Well, this is carbon number 1. This is a reference point. This is going down, right? So this is an alpha 1. And then what's the carbon on the other sugar? So what's the next sugar? So if you look at the next sugar, it's a 6-membered ring. It's a pyranose, right? Down, up, down. What's this? This one was D-galactose. That's D-glucose. That is correct. So this is D-glucose, right? Glucose, right? And what carbon is this? Which carbon is this? So this is number 1. This is 2. This is 3. This is 4. This is, hold on, 1, 2, 3, 4, this is 5 down here, and this one is 6. Okay, let me clean this up. So we've already established this is 1, and we've already established that this is alpha. So it's alpha 1. So then here, 1, 2, 3, 4, 5, 6. So it's an alpha 1,6 linkage. Okay, so we have a galactose bonded to a glucose in an alpha 1,6 linkage, and then the glucose is bonded to, what's this one? That's fructose, correct. So this is D-fructose, right? Fructose. And then if you notice, it's also involving its anomeric carbon, because this is the one that has the 2 oxygens, right? It's the acetal linkage. And this is, I hope you can appreciate, if you stand back from it, this is sucrose, right? So we already know that this is an alpha beta 1 to 2 linkage between those two. Okay? So you need to be able to look at these sugars and start quickly going, okay, this is galactose and it's bonded to an alpha this and beta that and all these types of things. We're going to do multiple examples now. So once you see 5 or 6, you're going to be all set. All right. So here is an important structure physiologically. We mentioned at the beginning of the discussion of carbohydrates that there's entities that are known as glycoproteins. These are proteins, structures that exist on the surface of cells. They're covered with carbohydrates. I didn't actually say it that way. I'm digressing a little bit. But we mentioned how carbohydrates are critically important structures on the surface of cells. It turns out they actually bind to proteins. And those proteins are called glycoproteins because the glyco means that they have sugars associated with them. And they're typically oligosaccharides of different structures with different linkages. So what actually identifies you as having a particular blood type is because your red blood cells, some of the proteins on their surface contain a set of oligosaccharides, and depending on which oligosaccharide it is, which monosaccharides it contains, and how they are linked, that then is what your red blood cells contain. That's what then defines your red blood cells as being either A, B, or O. Okay? So what we call the ABO blood group antigens are a collection of oligosaccharide structures that exist on the surface of your red blood cells, and depending on which red blood cell type you are, is what collection of oligosaccharides your cells are carrying. So over here is just a little snapshot of what the A antigen looks like. Okay? And then we give you some information as what's different in the O, what's different in the B. So let's analyze this entire structure so that you can start identifying these patterns. So if we start on the top left, this one over here, notice this is down, up, up. So this is coming from galactose. But notice there's an amino group instead of the regular hydroxy. And not only that, there's an acetyl group attached to that nitrogen. So we talked about this when we were talking about sugar derivatives. So this is actually an N-acetyl galactosamine that is serving as that structure. If you have blood type O, that piece is just gone altogether. You don't have it. So that's what's going to make a difference, right? So if you have A type, you have it. If you have O type, you don't have it, okay? So now let's identify the linkage, right? So if we notice, this here is my anomeric carbon. It's bonded to oxygen, and it's bonded to another oxygen, right? The question is, what is the type of linkage? So if you notice, this is carbon 1. Here's what defines it as D. This is going in the opposite direction. So this is going to be an alpha 1. The question is, what's the carbon in the other sugar? So it's the sugar that's sort of towards the middle, right? So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Notice it's on carbon 3. So this is an alpha 1,3 linkage between the N-acetyl galactosamine and this sugar. What sugar is this one? Well, if you notice, the oxygen's down, the oxygen's up, and the next oxygen is up. This also is coming from galactose. Here you're given that information, right? So it's N-acetyl galactosamine bonded to another galactose. That's smack in the middle of that whole thing, right? Everybody's with me? All right. So now that we've established that this is an alpha 1 to 3 galactosamine with N-acetyl galactosamine with another galactose. Now let's look at that galactose that's in the middle. Let's focus on that one. So this one, this is its anomeric carbon. This is pointing upward here, right? And it's in the same direction as this. And the one that's on the far right, down, up, down. So this is coming, and notice it's an amino and it's an N-acetyl. But this one is N-acetyl glucosamine. Why glucosamine? Because it's down, up, down on that structure. So how is that galactose in the middle linked with this one? Okay. So we've established that these are up, and this is carbon 1 on this one, and this is 1, 2, 3, 4. So this is a beta right here, beta 1 to 4 linkage. Everybody sees that? All right, and then the sugar that's on the far bottom, couple things. There's no CH2OH, and not only that, it's pointing downward. Okay, pointing downward. So this is an L sugar, it turns out, and it's also a deoxy L sugar. This happens to be L-fucose. You don't need to know L-fucose. That one you don't need to remember. That's a very specific, very unique thing. We're giving you that information. It's L-fucose, okay? It's one of those funky deoxy sugars, and it's an L sugar as well, so it's one of those funky things. Now, what type of linkage is that L-fucose forming with the galactose that's in the middle? So now we're trying to identify, hold on, we're trying to identify how these two are linked together. So this is the anomeric carbon of that one. That's the source, right? That's carbon 1. And it's bonded to carbon 2 of the galactose. Now, is it alpha or is it beta? Well, this is pointing upward. You may be tempted to say it's beta, but this is pointing in the opposite direction of the CH3, which is what makes it L. Because they're opposite, that's actually an alpha 1,2 glycosidic bond, okay? So this is alpha 1,2. Let's recap this. This one was alpha 1 to 3. This one was beta 1 to 4. And this one is alpha 1 to 2. Okay? And other than the fucose, which we would give you, you need to be able to stand back and identify, what is this? Well, this is down, up, up, and it has this thing. So that's N-acetyl galactosamine. What's this one? Well, it's down, up, up. That's D-galactose. What's this one? This is down, up, down, and it has that whole thing. That's N-acetyl glucosamine. And you need to be able to identify which carbons are bonded with which carbons and what type of linkages they are associated with. So just FYI, if you are B type, then this here, instead of being N-acetyl glucosamine, it's actually galactose. Okay, so that's what makes the difference for that one. So depending on if you're A, B, or O, that's what the structure looks like. This is actually bonded to a protein in the red blood cell, right? But this little piece is kind of like a little antenna that's on the surface of the red blood, like a little hand that's sticking out, right? And then depending on how many fingers that hand has, is how it's identified and that's what then classifies it as A or B or O. And if you're group AB, then you have both of them. You have both the A and the B antigen. All right. So let's look at some examples of substances and try to identify what sugars are involved and what type of linkages are associated with these sugars. So this is an oligosaccharide, has 4 sugars, so we call it a tetrasaccharide. So the question is, what's sugar A, sugar B, sugar C, and sugar D? So sugar A is what? So sugar A is glucose, right? Down, up, down, right? So this is glucose. I'm going to use gluc as the abbreviation. And the rest of them, hopefully you can appreciate that they're the same. They all are anyone? Fructose. So all of these are fructose, right? Let's use fruc for that. Okay. So then comes trying to identify the linkages. So what type of linkage is linkage number 1? So if you observe, it's these 2 carbons that are linked with one another, right? If you've been paying attention and you analyze what this whole thing is, this is technically a sucrose, right? That's then latched onto other things. 2 more fructoses are hanging off of that whole thing, right? So we already know that the bond linkage in sucrose, which is what that piece that I've circled on the or squared on the left is, it was alpha beta 1 to 2, right? So that one you should have recognized. Now let's try to figure out the other ones. I'm going to erase this to make it cleaner, right? So here, if you notice, it's bonded to this, right? So these bonds, number 2 and in fact number 3, this is 2 and this is 3, right, are identical. And it's also involving the anomeric carbon, well, actually the anomeric carbon of these 2, right? So this is our reference point. This is our origin, this one and this one. Let's focus on 2 first. So it's bonded from this carbon. What's the number of this carbon on fructose? Right here? Anyone? So that's carbon number. This is number 1 here, and this is number 2 here. Okay? Let me see if I have I don't have a fructose anywhere near this, but if you focus on this, never mind anything else that it's attached to. This was carbon number 1, because remember we had a CH2OH and then we had the ketone and then the rest of the structure. So this CH2 is this CH2, and then the ketone is what's forming the acetal. Okay, so this is 1 and this is 2. This is 1 and this is 2. This is 1 and this is 2. You can see it on the one that's on the end. Okay, so if you see that, then you'll notice this is carbon number 2, and it's wrapping around to carbon number 1 in the other sugar. So this bond is an alpha 2 to 1. Okay? The starting point is always the acetal. Whatever it is on the other sugar is what you write as the second number. Okay? So this is the starting point, the acetal, and this is the end point. Okay? So if you look at the number 3, it's exactly the same, right? So here's my acetal. That's my reference point. That's carbon number 2. And actually, it's not alpha, it's beta. That was my bad, right? Because if you notice, this is up. This is in the same direction. So this is a beta 1,2 glycosidic bond, right? This is up and this is up. So this is also beta 2 to 1 glycosidic bond. It's going from number 2 on this one to number 1 on that one. From number 2 on this one to number 1 on that one. And here it's going from number 1 on this one to number 2 on that one. And this is alpha, but this one is beta. Okay? All right. So some interesting information that you should be aware of if you are pursuing a degree in nutrition. Some of this discussion is going to be important for you. So sucrose is what we call table sugar. This is the standard for sweetness for a variety of different things. So in the grand scheme of things, just to compare sweetness and so that we can get whole numbers as opposed to fractional things, sucrose is assigned a value of 100 when you're comparing the sweetness of sucrose with the sweetness of other things. Okay, so this table here is giving you some information of different substances that are out there used as sweeteners. So all of these here are natural compounds. So again, if you focus on sucrose in the middle over here, that's given a value of about 100 or of 100. And there's different natural compounds that we know, that we use, that we are exposed to, that have different levels of sweetness. So if you go down the list, xylitol is one of these alcohol, i.e. reduced sugars that are used as artificial sweeteners. That one happens to have the same level of sweetness as glucose, as sucrose, excuse me. Turns out glucose is less sweet than sucrose, than table sugar. Galactose is as well. So this is why if you drink lactose-free, well, let's not go there. This is another discussion. It's a little bit sweeter than sucrose, less sweet than sucrose. So notice sorbitol. I also mentioned sorbitol is commonly used as a as one of these artificial sweeteners. That's actually the reduced product of glucose, significantly less sweet as well. And if you go down the list, there's different things. So this is why milk is not super sweet, because lactose is only 15 compared to 100. What I was going to say earlier about lactose is that this is why lactose-free milk, I'll just mention it briefly. If you've ever tried the lactose milk, it's significantly sweeter than regular milk. And it's because when you hydrolyze lactose into glucose and galactose, the level of sweetness goes up. Okay, so that's one reason why that can happen. I'm not sure how, if they actually manipulate the amount of lactose versus glucose and galactose, and if they take out some of that glucose and that galactose when they process it and put it onto the market. I honestly don't know that, but I have tried lactate milk. It tastes different, and I feel that it's a much sweeter than regular milk. No, you don't. You do not need to know the order of which sugars are sweeter and less sweeter, and none of that. You should have an idea, but so like the critical ones, like know how, for example, glucose compares to sucrose and things of the sort, and some of the things that I'm going to mention now, which are actually important, but not. You don't need to memorize that whole list and their numbers or none of that. All right. So if you go up the list, invert sugar is actually hydrolyzed sucrose. So if you continue up the list, you'll notice that fructose is sweeter than sugar, but glucose is less sweet. So remember, sucrose is glucose and fructose combined. If you hydrolyze it and break it apart, you've released glucose and fructose, and they've been mixed in equimolar amounts. There's 50-50 of each. Well, it turns out that one's less sweet, but one is considerably sweeter. So per gram, invert sugar, which is what we call hydrolyzed sucrose, is sweeter than regular sugar. Okay, honey, for example, is much sweeter as well than sucrose because of the fructose that it contains. Okay, and then at the top is one of these stevia glycosides. They are marketed as naturally occurring compounds, and you know, organic and all these other things, but natural compounds. You know, one day I had a fit in one of these tea shops in downtown Boston because, oh, we only offer stevia because it's natural. Oh, it's natural. Yeah, it's natural. You know what else is natural? Cocaine is a natural product that comes from leaves, just like stevia, and so is nicotine. So stop that and put Splenda and Equal and give everybody what they want as opposed to this stevia stuff. Anyway, I hate stevia. To me, it's bitter. I don't like it. I like to have my options. That's my little rant on stevia. All right. And then, of course, there are the artificial sweeteners, which are man-made laboratory concocted products. So some of them are shown here. Again, the relative sweetness is back to comparing it with sucrose. If we go back one slide, again, you'll notice these stevia glycosides are about 3 times as sweet as sucrose. If we go to the artificial sweeteners, then these are orders of magnitude, many, many, many more times sweeter. So this one is 30 times sweeter, right? You just have to drop 2 zeros because remember, sucrose is 100. It's about 30 times as sweet as sugar. This one is another one, is 200 times sweeter than sugar. And then our friend aspartame is 180 times as sweet as sugar. So these two are not sold commercially that you can buy them off the shelves at the supermarket. They're used in industry applications. And it turns out some of these compounds over time have been removed from the market because they've been noticed to cause all kinds of problems, including cancer and all kinds of things. Anyway, aspartame is still active on the market. Anybody know which one is aspartame? Is it the blue or the pink or the yellow? Nobody knows? So aspartame is the blue. No, the pink is another one we're going to talk about. So this is the blue, which is the original commercial name is Equal, right? That was the original brand name of the company. Once the patent ran out, then half the world can go out and make it for cheaper. And if you look at the structure of aspartame, we haven't talked about amino acids yet. That's the next chapter. In this case, this is actually 2 amino acids linked together. There's technically, this would release methanol if is ingested in large amounts, but because it's 180 times as sweet as sugar, you only need smidgens of the stuff. So there's no harm, at least structurally speaking, from taking aspartame, because all you're releasing is 2 amino acids, which are integral parts of the human body and part of your diet. The only concern that you can raise is that there's bits of methanol generated. Again, the amounts of aspartame that you would ever intake in a single dose is so minuscule that the amount of methanol that would ever be produced is really not an issue. So the next one is the pink stuff. This is saccharin. So saccharin is 300 times as sweet as sugar. So you really need a smidgen of this stuff to really trigger your taste buds. And the one at the bottom is 600 times as sweet as sugar. What do you notice about the structure of this compound? This is the yellow stuff. This is Splenda. That's the original Splenda. Oops, sorry. I'm going to have to rewrite it again. Splenda is the original brand name. Again, the patent has run out. Correct. So it's exactly the same skeleton as sucrose, but it's been chemically altered to several of the hydroxys. This one and this one and this one, 3 of them, have been replaced by chlorine. It turns out that this one is actually a galactose. You notice that this is down, up, up, right? So it resembles sucrose very closely. It turns out it's a variant, and because it has that structural resemblance, it actually triggers your taste buds, but on steroids, 600 times sweeter. So minuscule amounts of these things are needed to trigger your taste buds, okay? So let me just talk a little bit about these items that were on some of these lists, just to give you some information. So why is hydrolyzed sucrose called invert sugar? It turns out that when you hydrolyze sucrose, as I said, you generate glucose and fructose. So both of these are chiral substances. Glucose is dextrorotatory. Fructose happens to be levorotatory. And it turns out that the magnitude of the angle of rotation for fructose on the negative side is a larger value than the positive rotation of the glucose. So the net result is a negative rotation for the mixture. And it goes from being dextrorotatory, sucrose is dextrorotatory, but the mixture of glucose and fructose is levorotatory. So we call it invert sugar because the rotation has been inverted in the opposite direction. It's merely the presence of the fructose combined with glucose. Turns out because it's sweeter, you need less. So it turns out that per gram you need less, so it's actually cheaper. We've talked about briefly high fructose corn syrup. This is actually glucose that has been treated enzymatically with an enzyme. Well, enzymatically, the enzyme is called glucose isomerase, and it actually converts not necessarily all, but some of the glucose to fructose, right? So notice it goes from a 75 sweetness relative to sucrose to 170, right? So again, much sweeter, you need less to sweeten. The soda companies and all kinds of food companies loved this stuff because it was much cheaper to sweeten things because you required much less material. We've talked about sorbitol, is that reduced version of glucose. Again, it's, as we've mentioned, these substances are not well absorbed. It has minimal glycemic index impact. It doesn't really impact your blood sugar. So this is why it's used as a sweetener for foodstuffs for diabetics. They get the sweetness. Again, there's a little aftertaste if you've ever tried these, you know, sugar-free cookies and sugar-free chocolates and whatever is out there. They're okay. I mean, if you're diabetic and you have a sweet tooth, then that's it. That's all you have, right? But if, you know, some of these substances can have a little bit of an aftertaste. So let's talk a little bit about these artificial sweeteners. Again, they are non-carbohydrate organic molecules that they simply interact with your sweetness, with your taste buds, and they trigger the taste of sweetness. So some of them are ionic. Some of the ones we mentioned over there were ionic compounds, and that actually helps them dissolve in the saliva and get into your taste buds and trigger that response. Some of them have an aftertaste, and as we've said, some of them have been taken off the market. So that sodium cyclamate that we were talking about, that actually has been banned since 1969 because of concerns with health. The sodium saccharin, which is the pink stuff, actually required for many years to have a disclaimer that this substance has been known to cause cancer in laboratory animals and rats and all kinds of different things, and mice and whatever it was. That was later removed because it turns out that it's been demonstrated that that really has no association with cancer development in the population. Interestingly, back in the days of which there was little concern to safety in the laboratory, people used to do all kinds of very bad things in the lab, including drinking and smoking and not using gloves and all kinds of things that today would be considered completely unacceptable. So it turns out sodium saccharin was discovered when somebody was working in the lab and they were working with saccharin and they happened to put down their cigarette as they were working on the bench. Oh, let me have another puff of my cigarette. Oh, my cigarette is all sweet. Why is this sweet? Well, because it got contaminated with the compound they were working with, and it turns out that it was saccharin, and that's how saccharin started. Somebody discovered that sweet compound, not supposed to be tasting anything in the lab. Well, if you're putting your cigarettes down on your bench and then putting them back into your mouth, what do you expect, right? So that's how that whole thing took off. It's been known for a while. And then another gaffe over here with Splenda. As we mentioned, it's very similar to sucrose, actually not identical if we notice that chlorine is in the wrong place. So that's a sort of a galactose type of thing. But there's simply the replacement of the hydroxys with the chlorines, and this is another one. The person, the graduate student, turns out, was working in the lab, and the principal investigator tells the student, test it, and he understood taste it. Well, you don't argue with your PI in 1967, right? So he went and tasted it, and it turns out that it was Splenda. He was working with sucralose, the sweetest thing on the planet, right? And that's how that whole thing took off, right? And now whoever discovered that whole thing is probably smiling all the way to the bank at this point. So again, we mentioned the stevia glycosides. Please, we just urge you to go read on pages 400 and 401 in your textbook to learn a little bit more about the stevia glycosides. All right, so let's do a little bit of an introduction of polysaccharides, which are the largest of the structures that involve carbohydrates, and we can divide them into several categories, as we're going to see. So when we're speaking of polysaccharides, we also call them complex carbohydrates. These structures have several important physiological functions. First, they provide a structural and energy depot functions, meaning that there are many carbohydrates, polysaccharides, that are integral components of the structures of our cells and our tissues and things of the sort. And many of them will also provide as a source of energy, as a storage form of energy. That's what we call it, an energy depot, in between meals. So this is when we're going to talk about glycogen, among other things. So we classify them broadly into two categories. Homopolysaccharides are composed of only one monosaccharide that repeats again and again and again and again and again, the same one, nothing else. The ones that are important that we're going to discuss: cellulose, which is dietary fiber; amylose and amylopectin, which is plant starch. It's a mixture of two things: starch, can't write today, starch, and then glycogen, which is technically called animal, in quotations, starch. It has similarities with the plant starches that we're going to talk about. And then there are the heteropolysaccharides. They're called hetero because they're heterogeneous. They contain more than one distinct monosaccharide scattered throughout the structure, so they're heterogeneous in that regard. We'll briefly mention hyaluronic acid and chondroitin sulfate. These are important in connective tissue, and all of our connective tissues contain different forms of these compounds. And then heparin, particularly those of you who are in the nursing program, you're going to be learning a lot about different forms of heparin. This is used as an anticoagulant, and depending on how many sugars are bonded and the level of branching, which will become clear when we actually get to the discussion, and the size of the molecule and the whole thing, there's different tiers of heparin: high molecular weight heparin, low molecular weight heparin, highly branched, less branched. They come in all kinds of formulations. You will be taking care of patients in intensive care units and that are in the hospital, patients that are bedridden, patients that are post-surgical. There's all kinds of different formulations of heparin used in all of these scenarios, okay? So very briefly, and we'll end with cellulose today because I think we have about another 2 minutes. Cellulose is the main structural component of cell walls of plants, and it is a repeating pattern of glucose after glucose after glucose after glucose. It's a homopolysaccharide, and they're all linked in a beta-1,4 glycosidic linkage. So remember earlier how I said we do not have the enzymes to break beta-1,4 glycosidic bonds? The exception is lactase, which some of us may not have. If you look at cellulose, here's a beta-1,4 and another beta-1,4 and another beta-1,4. We do not have the enzymes to break this down into the corresponding monosaccharides. So all of those plant components, which are important, they're significant components of all fruits, vegetables, and any plant products. All of that ultimately gets broken down, not into pieces, but everything else that can be broken down gets taken away. The cellulose is left behind to the bare bones, and these are very long polymers accumulate in your intestines. They actually provide volume and bulk to the stool as it's traveling down. That stretches the wall of your intestines. It promotes proper motility. It promotes proper absorption. It promotes proper digestion. And that ultimately is what we call dietary fiber. Okay? All right. We'll continue with the rest of this discussion next week. Remember, we have a quiz on Tuesday. It does not include any of this stuff that we've been talking about today. And I hope everybody has a great weekend.